Hey everyone, and welcome. Today we're going to talk about one of the most elegant yet powerful tools in programming, the set. Now it might sound simple, but its one core principle, handling only unique data, makes it an absolute secret weapon. So let's dive in and see how it works. Okay, so picture this. You're planning a party and you're jotting down your guest list. And whoops, you accidentally invited Alice twice. In the real world, that's not a big deal. But in programming, oof. Duplicate data can cause all sorts of bugs, it wastes memory, and it just creates messy, inefficient code.
So, that brings us to the big question, right? When you have a collection of items, how do you effortlessly make sure that every single thing in it is unique? How do you filter out all the noise and just get down to the pure, distinct data?
And this isn't just a party planning problem, It's a fundamental challenge in computer science. We can call it the duplicate data dilemma. And it's something developers bump into constantly, whether they're processing user IDs, tracking inventory, or analyzing massive data sets.
And this is where our hero comes in, the set. A set is a data structure with one simple, non-negotiable rule. It only stores unique elements. If you try to add an item that's already there, it just doesn't. Think of it like a bouncer for your data, making sure no duplicates get inside.
And this isn't some brand new programming trick. The whole concept of a set comes straight from mathematics. It's a foundational idea, which just proves that the need to manage unique collections is a really timeless, fundamental concept.
To really get what makes a set so special, let's compare it to something we're all familiar with, an array or a list. An array will happily take duplicate values, and it keeps everything in a very specific order. A set, on the other hand, absolutely enforces uniqueness and, in its most common form, doesn't guarantee any order at all. And that very trade-off is the secret to its power.
So we know what a set does, but let's just make it official. A set is an unordered collection of distinct items. I like to think of it as just a bag of things, where you can't have two of the exact same thing, and the order you put them in just doesn't matter.
So how does this set actually enforce this rule? Well, there are two main strategies. The first is a sorted approach, often using something like a binary search tree. When you add a new element, the set quickly zips down the tree, going left for smaller values and right for larger ones. If it finds an empty spot, it'll place the new element there. But if it finds an identical element that's already in the tree, it just stops. No duplicates allowed. The second method is the hashed approach, which uses a hash table. This is what you'll see in languages like Python and Java. Here, every element gets converted into a unique address, or a hash. The set instantly checks that address. If the spot's empty, great, the element goes in. If it's not, that's called a collision, and the set has clever ways of dealing with that. The key thing to remember is that this whole process is incredibly fast.
Now this brings us to a really crucial trade-off. The tree-based approach keeps your elements sorted, which is nice, but its speed, which we call O of log n, slows down just a tiny bit as the set gets bigger. The hash table approach, on the other hand, is completely unordered, but its speed is O of 1 or constant time. And this is the magic part. It's like having a dictionary where you can flip to the exact right page instantly, no matter how many words are in it. Adding an item to a set of 10 million takes pretty much the same time as adding to a set of 10. It's wild.
So, we've just seen the two main ways that sets enforce that all-important uniqueness rule. It's either through that organized, sorted tree structure or a super fast but chaotic hashing system. Both get the job done, but they make you choose between two different priorities, order versus speed.
Now, because sets are rooted in math, they come with some incredible built-in superpowers. The first one is the union. A union of two sets basically combines them into a brand new set that contains every unique element from both of the original sets.
And this shows it perfectly. If set A has 1, 2, and 3, and set B has 3, 4, and 5, their union is simply 1, 2, 3, 4, 5. See that? The number 3 was in both of the original sets, but it only appears once in the final result. That's the set's uniqueness guarantee, right there in action.
All right, next up is intersection. This operation looks at two sets and creates a new one containing only the elements that appear in both of the original sets. It's all about finding the common ground.
So, using our same sets, A with 1, 2, 3, and B with 3, 4, 5, what's the intersection? Well, the only element they both share is the number 3. So their intersection is just a new set containing 3. It's a really simple way to find what two collections have in common.
And our third superpower is the difference.
This does exactly what it sounds like. It creates a new set with all the elements that are in the first set, but not in the second one. You can really think of it as subtracting one set from the other.
Let's look at our example again. If we want the difference of A minus B, we start with everything in A. That's 1, 2, and 3, and we remove anything that's also in B. The only thing they share is 3, so we take that out. What are we left with? A new set with just 1, 2.
So there you have it. Union, intersection, and difference. And these aren't just abstract ideas from a math class. They are highly optimized operations that let programmers compare and combine collections of data with incredible efficiency.
Okay, let's see how this all works in practice. This is a scene you see all the time in programming. A Python list that's just full of duplicate numbers. It's messy and it's inefficient.
Now watch this. We can take that messy list and with one single elegant command, turn it into a set. And just like that, poof, the duplicates are gone. We're left with a clean, pure collection of unique values. This is exactly why programmers love sets. It takes a common, tedious problem and solves it instantly.
And this power goes way beyond just cleaning up lists. Sets are really the backbone of many critical operations. They're used for super fast membership testing, like checking if a username is already taken. They power the database indexes that make our searches so quick. They're even essential for solving complex problems with networks and maps.
So, from a simple mathematical concept to a cornerstone of modern software, the set really proves that sometimes the simplest ideas are the most powerful ones. They bring a ton of efficiency and clarity to our code.
If there's one technical detail you remember from all of this, make it this one: O of 1, or constant time. For the most common kinds of sets, checking if an item exists is just as fast in a set of 1 billion items as it is in a set of 10. That is just mind-bogglingly efficient.
And that leaves us with a final thought. We've seen that the incredible speed of the most common type of set comes from giving up on order. But order can be really important, right? So when would you, as a programmer or a problem solver, choose to make that trade? When is a predictable, sorted list more valuable than pure, unadulterated speed?